About solutions and molarity. And remember, molarity is moles per liter. Remember, it is a formula that you could kind of rearrange. So if you want liters, that is moles divided by molarity. If you want moles, that is liters times molarity. And that is a really important relationship, as we talked about. Whenever you use the molarity by itself and you are using volume, you do need to make sure that the volume is always in liters so that it cancels out correctly. Again, if you multiply by milliliters, you will not be getting probably the unit you're looking for, which is most likely moles. You'll actually be getting millimoles. Remember as well, getting rid of the big M in calculations is also a preferred way of doing calculations. So as we talked about, if you have 4.5 molar sodium chloride, you really do want to sort of get rid of this big M and use both the units present, moles per liter of sodium chloride. Remember that the number always stays with the moles part. It's always per 1 liter. And you could use this really more dimensional analysis way, as we talked about, and you could flip it around and use it really as a conversion factor. And the reason really you should use both units is I can't tell you how many papers I've seen over the years where people just use the big M and they're really not sure what the unit is. They oftentimes think it's moles because it starts with an M, I suppose. They have usually no idea about the volume aspect of the calculation and stuff like that. So again, you have probably a better shot there if you kind of take a dimensional analysis approach and you show both of those units. At least you can see where the volume is on top or bottom and not forget about it. That means, for example, if you have the liters and you want moles, you would multiply by the molarity. Here, the liters would cancel if you take a more dimensional analysis approach. And obviously, you would divide by whatever's on the bottom. That would get you moles. If you are looking for moles, or if you're looking for liters really, and you have the moles, you could also use the molarity in the opposite way, put the moles on the bottom, the liters up on top. Again, going to multiply and divide in this particular case. The moles will cancel and that will give you liters. So it is highly recommended that you do it dimensional analysis way. It also, frankly, takes care of all the did I rearrange this thing correctly sort of questions. Because if you just do dimensional analysis, opposites cancel, multiply whatever's on the top, divide by what's on the bottom, you don't have to worry about rearranging the equation because it'll just kind of do the math for you. So that's, again, a better approach at it. Any questions on any of that stuff there we talked about last time? All right, continue on here. Another sort of topic we talked about last time was the idea, especially with ionic compounds, of the concentration of just the ions. So if we have an ionic compound like this guy here, or a solution of an ionic compound like sodium sulfate and 0.75 molar potassium chromate. Again, remember that sometimes we may not be interested in the concentration of the whole ionic compound, but we may be actually interested in the concentration of the ions that are floating around that solution. Remember, because they are ionic, they are going to be a strong electrolyte, which means if you put sodium sulfate in, you're going to get a couple of sodium ions and a sulfate ion floating around in that solution. So the way molarity works, as we talked about, is you want to think about how this is going to break apart. This would break apart into a couple of sodium ions and a sulfate ion. And because this is 1.2 molar, we could do really a stoichiometry relationship. It's a 1-to-2 relationship in terms of the whole thing in the sodium ions. How that affects the concentration is, as we talked about, you essentially would multiply the molarity by 2 in this case. And for the sodium ions, we would have a concentration of 2.4 molar. And if you did it for the sulfate, it is a 1-to-1 relationship between those two. And basically, you would take 1 times the 1.2 molar, giving you 1.2 molar of sulfate. So as you can see here, the solution is actually twice as concentrated in sodium ions as it is in sulfate ions. And that's what we see here when we draw the picture. You got 2-for-1 situation. So again, twice as concentrated in terms of the sodium. Same thing would happen on the bottom here. This guy would break apart into 2 potassiums and a chromate. And if we know the concentration of this guy, we could do the same approach. It is a 1-to-2 relationship here with our potassium. So how that affects the concentration is we take 2 times the concentration, and that's going to give us 1.5 molar for our potassium ions. When we look at the chromate, it is a 1-to-1 relationship, which means it is 2 times 0. I'm sorry, 1. There we go. 1 times 0.75 molar. Going to give us 0.75 molar for our chromate ions. Once again, that is sort of the quick way that you can get the concentration of ions. If you know the concentration of the whole ionic compound, basically whatever the coefficient is that it breaks apart into, you multiply the concentration by it. A reminder that really that is the short way of the long version of that calculation, which would be 1.2 moles per liter of sodium sulfate. And again, doing a mole to mole relationship, it is a 1 mole of the whole thing gives us 2 moles of the sodium ions. Moles of the whole thing cancel, gives us 2.40 moles per liter of sodium ions, hence why we multiply by 2 in this case. So that's really the long version of that calculation where you basically just multiply the coefficient by the molarity. Any questions on that there? All right, so let's take a look here. So why don't you try this one? How many moles of calcium and chloride would be present in 42 milliliters of a 0.35 molar calcium chloride solution? I'm going to take a couple minutes to see what you come up with here. Given to us, we have the volume here of 42 milliliters. We do have the molarity of the whole thing. Again, I'm going to convert it into moles per liter here of our calcium chloride. But in this particular case, we are not interested really in the moles of the whole thing. Bless you. We're actually interested in the moles of each of the ions. You could actually approach this one of two ways. You could keep it together and then go to the ions at the end, or you could just go to the ions up front. And that's what I'm going to do. I'm going to get the actual concentration of those ions up front, and I know when it breaks apart, I get a calcium ion, and I will get a couple of chloride ions in this case. And as we just did in that previous example, I know that this is 0.35 molar, and it is a 1-to-1 relationship between that and the calcium, which means really my calcium would be 1 times 0.35 molar, or that will give me 0.350 moles per liter of calcium ions basically there. When I look at the chloride, it is a 1-to-2 relationship. So I do need to multiply my concentration by 2 here. And that will get me 0.7 moles per liter of chloride ion. Again, it's a 2-for-1 deal here. So we got twice as much chloride as we do calcium in this case. So we have twice the concentration. At this point, I really could just use the molarity sort of formula here for each of the ions. I have the molarity, I have the volume, I could get the moles here. And again, the moles would equal liters times molarity in this case. Once again, I always need to make sure my volume's in liters when I am using molarity by itself. So we'll convert that 0.042 liters here in this particular case. So to do the moles of calcium ion, I'm going to take a dimensional analysis approach, which means I'm going to start with my volume here. I'm going to use my molarity as a conversion factor, and it's actually good the way it's written there. We could go 0.350 moles per liter of calcium. The liters will cancel, and that's going to get us here 0.042 times 0.35, 0.0147 moles of calcium in this case. We'll basically do the same calculation here for chloride. So our moles of chloride in this case, 0.042 liters. We want to use our molarity of the chloride, which is 0.7 moles per liter of chloride. The liters will cancel. Going to get us 0.0294 moles of chloride. If I wanted grams of each of these, I could use the molar mass of calcium and chloride and get to grams. Any questions on that calculation? As I mentioned before, you could have just used the molarity of the whole thing, got the moles of the whole thing, and then did like a mole-to-mole relationship to get the moles of each ion. And again, it will come out the same way. Any questions on that one there? Okay. So then let's talk about another process that is very commonly used, and that is dilution. And dilution is basically when we add more solvent. Now, water is oftentimes used with a dilution, and people sometimes talk about waters always being the solvent. A reminder that water may not always be the solvent, but we do oftentimes use water, especially with ionic compounds. The reason for that is we have a solution that has a very high concentration, and we want to use a more dilute solution. So adding water, for example, the solvent, will accomplish that for us. And that is because the molarity here is really moles of solute divided by liters of solution. And as we've talked about, a solution is the solute plus the solvent. And what you do when you add more water or solvent to it is you're actually increasing this number, which is the bottom number here. And now you're going to be dividing by a bigger number on the bottom, and that's going to bring your molarity down, basically. So that will bring your concentration down because you'll actually end up with a larger number for the volume of solution. And again, that's going to bring it down. The solute actually doesn't change, and that's actually the stuff that reacts in a solution. So the moles of solute before you do the dilution and after the dilution will be the same. So that really doesn't change. It's just that amount of solvent that you add, and that changes the volume of solution. It lowers the molarity. Now, how do you do that? Many ways you can do it. You can use a volumetric flask. As you may be aware, volumetric is expensive. It usually has one line on it, and usually that is a double decimal place there when you do the reading. So you could add some water, add your more concentrated solution to it, top it up here to the line, and close the lid, give it a mix, a little shake maybe. And at that point, you will have diluted it again by adding that extra water. It's going to lower the molarity of that solution. Now, there is a formula that you could use to calculate that, and that is M1V1 equals M2V2. That is the dilution equation. And this is usually before the dilution. And this is usually after the dilution. M here is molarity, V is volume. In this particular equation here, you can, if you want, leave the volume here in milliliters and it will work out okay. The reason it will work out okay, for example, if you solve for M1, that would be M2V2 divided by V1. If this is a milliliters and this is a milliliters, you will get back to molarity. Everything will work out okay. If you're solving for something like V1, that would be M2V2 M1. The M's will cancel and leave you with volume in milliliters. You could also convert it to liters as well. A reminder though that if you are using volume and molarity by itself, not in a dilution situation, you should absolutely positively always convert the volume into liters so everything cancels out correctly. Again, if you multiply milliliters by molarity, you will end up with millimoles, not moles. So you'll be off by a factor of 1,000. So in most cases, you want moles. So always convert to liters when you're using molarity by itself. But if you are using the dilution equation here, you can leave it in milliliters. Everything will work out okay. Nowadays, though, they like to teach people C1 V1 equals C2 V2. And C here is concentration. And obviously V is volume still. And the reason for that is, technically speaking, you could use any concentration unit you want in this formula. So we talked about like percent mass to mass, percent mass to volume, percent volume to volume. You could actually throw those into this equation and it'll work out just fine. So you can actually use it for any concentration unit. But since molarity is probably the most common unit of concentration, most people roll with the M1 V1 equals M2 V2. And again, you can actually do it either way. Any questions on that there? So let's take a look at this one here, which is what is the volume of 19 molar sodium hydroxide that we have to prepare 1 liter of 0.15 molar sodium hydroxide. So we're starting with sodium hydroxide, which is more concentrated than what we want to make, which is also sodium hydroxide. There is no real reaction or anything happening in this case. So just to explain again what's going on, we basically have a bottle sitting there of 19 molar sodium hydroxide. And what we want to make is a new beaker or whatever that has a total volume of 1 liter or 1,000 milliliters. And it should have a molarity of 0.15 molar. So this is definitely a dilution sort of problem. We could list what we have. Usually the more concentrated number is our ones. And here we don't have. We do have M2, which is what we want to make. And here we have our V2, which is 1 liter or 1,000 milliliters in this case. So we do want to use our dilution equation here. M1 V1 equals M2 V2. Solving for V1, we're going to divide that guy to the other side. M2 V2 M1. Putting in our numbers here, we end up with 0.15 molar, 1 liter, and we started with 19 molar. The molarities will cancel at this point, and we will end up with 0.15 times 1 divided by 19. We'll call it 0.0079. And my units here are going to be liters because I did leave this in liters. That is roughly 7.9 milliliters of our sodium hydroxide in this case. So what does that number sort of really represent? That number represents, when you solve for V1, how much of the more concentrated solution you would take out and pop into your new container, and here's 7.9. Now at this point, I really want to end up with a total volume of 1,000 milliliters. The rest here is going to be water. Should I put 1,000 milliliters of water in there? The answer is you shouldn't if you want to make the right solution. If I put 1,000 milliliters of water in there, I already have 7.9 milliliters. That's going to give me actually a total volume of 107.9 milliliters, which is not going to give me the molarity that I want. So one of the important things to figure out when you're making a solution are, a lot of times in these questions, is they sometimes will ask you what is the volume of water that you need to add to actually make the solution. And that is going to be our final volume minus our initial volume, or really our V2 minus our V1 in most cases. And that is going to be, in this example, I'll use the milliliters. 1,000 milliliters is where we want to end up. We added 7.9 milliliters already. That means roughly here we need to add in there about 992.1 milliliters of water. We would do that. We would add 992.1 milliliters of water. That will give us a total volume of 1,000 milliliters. At this point, we would carefully mix it. And you then should have a solution that has that molarity there of 0.15. Any questions on that there? So I would say that's a super common sort of question that is asked in dilution problems, is kind of like how you make the solution or how much water you need to add to get this thing diluted to the proper concentration. Any questions? All right, why don't you try one then here? What volume of water is needed to prepare 500 milliliters of 0.25 molar calcium nitrate solution from a 5 molar solution? Okay, let's take a look. So kind of a similar situation. Here we have a more concentrated 5 molar solution. And we do want to make a new solution that has a volume of 500 milliliters and a molarity of 0.25 molar. So once again, here we could use our dilution equation to figure out how much of this guy we need. So M1 V1 equals M2 V2. Again, this is basically M1. This is our V2, our volume, and our M2 in this case. So putting in here, we'll solve for V1 again, which is M2 V2 M1. Taking 0.25 molar, 500 milliliters, divided by 5 molar. Molarity here will cancel. Again, I left my volume in milliliters, which is okay because I'm using this equation. In this case, it just means my answer will be in milliliters. So 0.25 times 500 divided by 5 gets me 25 milliliters. Once again, though, that is actually not the answer to this question. 25 milliliters is actually the amount of calcium nitrate that you need to take out from the more concentrated solution to transfer over. We do want to know how much water we need. So to figure out our volume of our water, our final volume here, our V2, which is 500 milliliters, minus how much we already put in there, which is 25. That means roughly there we're going to need about 475 milliliters of water. That will give us our 500 milliliters total. And once again, once you mix that together, you now should be sitting with a solution that has 0.25 molar. Any questions on that one there? So again, you want to make sure you read these questions definitely careful. They very often, like I said, sort of ask for those type of things, like how much water or something like that that you need to add. Any questions on that? Okay. So the next thing we're going to talk about is stoichiometry that involves really solution or solution stoichiometry. And really, as we saw with gases, as we saw with sort of regular basic sort of stoichiometry problems involving grams and moles, it's really all the same steps. So you'll still follow our 4 steps, which is we want to balance the equation. We want to convert to moles. We still always, 100% of the time, when we are looking at some type of stoichiometry problem, we do want to determine, is it a limiting reagent problem? So remember that for it to be a limiting reagent problem, you need to have enough information given to you in the problem to be able to calculate the number of moles of each reactant. So if you have a way to get to the moles of each reactant based on the information given to you in the problem, then it is a limiting reagent problem. If you do not, then it is a basic stoichiometry problem. You can skip that limiting reagent step. We would then do our mole-to-mole relationship using the limiting reagent, and then we're going to take our moles to some other unit. So how does sort of solution, molarity, and volume all play into that? Well, pretty much most of the time at step number 2, you would be solving for moles, which would be liters times my molarity, and that's probably a very, very common way to get to the moles. I would also say at the end of the calculation, there's kind of 3 endings you usually could do. You could do grams like normal, which is molar mass. You can use molarity again, but in this case, one of the ways you could actually solve for the molarity, and very commonly we look for volume, which would be moles divided by the molarity. So I would say those are 3 sort of common endings of this, and probably in a lot of cases, especially if you're doing solution stoichiometry, a good number of times you're going to probably either be calculating the molarity, maybe like you did in the titration experiments, or you'll be looking for the volume here, or how much volume. You can also look for grams if you're doing some type of precipitation reaction, or maybe you're forming something that is a solid. Any questions on that there? So let's take a look at one here and see how we get to where we need to go. So we want to calculate the mass of solid sodium sulfate that's needed to be added to 250 milliliters of a 0.2 molar solution of barium nitrate to precipitate out the barium as barium sulfate. We also want to know the barium sulfate mass that is formed. So here it is, a stoichiometry problem. Clearly, we do not have an equation. So that is definitely where we want to start. So we have everything in words. As we've talked about previously, we want to make sure that we get the correct formulas first and then balance. So we want sodium sulfate. Sodium is +1, sulfate is -2, and that gives me a proper formula of Na2SO4 that needs to be added to barium nitrate. Barium is +2, nitrate is -1, which means when I put that together properly, I should have a formula that looks something like this, BaNO3 2. This also should look very familiar to you. This is a double displacement reaction, which means our partners are going to switch here, basically. So we do want to make sure we put the right formulas together. So barium is +2, sulfate is -2. That gives us a BaSO4. And remember that sodium is actually +1 and nitrate is -1, which means we actually get this as the proper formula. Again, we do not get the Na2NO32 because that's just made up. Yes, so remember, proper formulas first. Now that we have the proper formulas together, now we could balance it to take care of all the extras we don't have. And in this case, we could put some coefficients in there. And that looks like maybe I just need a 2 there. And I think that's it, actually. That's the only place I actually do need 2. Any questions on how I got to the equation here? Now, taking a look at what was given to me, we're looking for the mass here in one problem. And we do have 250 milliliters of a 0.2 molar solution, which again is our moles per liter. And we're also going to eventually look for the grams of this guy as well. So first off, this is not a limiting reagent problem because really the only thing we could get moles from is this guy. We cannot get moles from the other guy because we're actually looking for how much of the other guy it is. So this is just a basic stoichiometry problem. So that's how we're going to approach it. We are going to use this information to get to moles. So instead of using the molar mass, we're going to use the volume and the molarity to get to moles. Because I am using the volume and molarity here by itself, my volume needs to be in liters. So again, it needs to be in liters here. So you're going to divide that by 1,000, which would give you 0.25 liters. We're going to use our molarity where we can see both of the units. So 0.25 moles per liter here of our barium nitrate. Liters are going to cancel, and that's going to get me here 0.25. Actually, it was 0. There, I looked at the wrong number. That was 0. Times 0.25 times 0.2, going to give me 0.05 moles of barium nitrate. At this point, it really is just a stoichiometry move. We're at barium nitrate, but we do want to get over here, so we want the mole-to-mole relationship between those two, and it is a 1-to-1 relationship from the equation. That makes the math not too bad, so that's going to give me 1 mole of barium nitrate, 1 mole of sodium sulfate. Those are going to cancel, and I'm going to end up with 0.05 moles of sodium sulfate. I can again here use the molar mass from the periodic table to convert that into grams. So that is 2 sodiums at 22.99 from the periodic table, plus a 3207 from the periodic table for our sulfur, and 4 times 16 for each of the oxygens. That is going to give me a molar mass of 142.1 grams per mole. Again, the moles are going to cancel, and that will get me here. I need to put in there 7.1 grams of sodium sulfate in this case. First off, any question on that first part of the calculation there? Hopefully you can see it is our 4 basic steps. Balance the equation, convert to moles, mole-to-mole relationship, and moles to some other unit. So again, all the same 4 steps. In this particular problem, they also wanted to know how much product that we would produce. So we're also interested in how much of this guy we would produce. We really would just start the same way. And in this case, we could balance the equation. We can convert to moles, and we could actually just pick up at that point. And we already know we will get 0.05 moles of barium nitrate. We can now do the mole-to-mole relationship between barium nitrate and our product, which happens to also be a 1-to-1 relationship, which is nice. So for every 1 mole of barium nitrate, there is 1 mole of our product, which is barium sulfate. The moles are going to cancel 0.05 moles of barium sulfate. Again here, we could use the molar mass from the periodic table. Barium is 137.3, I hope, plus 3207, which is sulfur, plus our 4 oxygens there. There are 16 each. Looks like a 233.4. So taking this here, using the molar mass from the periodic table, 233.4 grams per mole of barium sulfate. And that's going to get us roughly 11.7 grams of barium sulfate would be produced. By the way, that would be a theoretical yield, as that's a product, and that would be the theoretical yield in grams. That would be the theoretical yield in moles, right? So again, because that is a product, that could also be your yield in this particular case. Also, really the same 4 steps. Balance the equation, convert to moles, mole-to-mole relationship, moles to some other unit here. Any questions on that particular one there? So let's take a look at another one here together and see what we got going on this one. We want to calculate the mass of a white solid, calcium carbonate, that forms when you mix 25 milliliters of 0.1 molar calcium nitrate with 20 milliliters of 0.15 molar sodium carbonate. This again is a stoichiometry problem, so we do not have an equation. That is where we should start. So in this case, we are mixing calcium nitrate with sodium carbonate. This again should look familiar to you. It is again a double displacement reaction where they're going to switch partners here. That's going to form our calcium carbonate, as calcium is +2, carbonate is -2. And again, we're going to get the proper sodium nitrate, NaNO3. No weird numbers with that, right? Now that we have the proper formula, it is time to balance. And once again, here it looks like just a 2 right there will take care of business in this particular case. Now we want to kind of look at the information given to us in this particular problem. For the calcium nitrate, we have 25 milliliters of 0.1 moles per liter. For our sodium carbonate, we got 20 milliliters of 0.15 moles per liter, which is the molarity. So hopefully you can see from this that I can get moles from this guy definitely, and I could get moles from this guy as well. That tells me this is actually a limiting reagent type problem. So you do have to, in this particular case, do that limiting reagent calculation. And a reminder that it is a calculation. You can't just like choose the smallest, right? So you actually have to do it based off of some type of calculation to determine which one's the limiting reagent. So we need to get our moles of each of our starting guys here. Once again, we do need to convert to liters. So our moles of calcium nitrate will involve 0.025 liters. That is dividing our milliliters by 1,000 to convert it into liters. I'm going to use my molarity like it is there. So 0.1 mole per liter. Liters are going to cancel. We're going to multiply the top there. That's going to give us 0.0025 moles of calcium nitrate. We are again going to do basically the same calculation for our other reactant, which is sodium carbonate. Also converting into liters, so 0.20 liters times the molarity. 0.15 moles per liter here. Liters are going to cancel. Going to get us 0.02 times 0.15. 0.003 moles of sodium carbonate. This again is very much the same idea as what we did previously, where we just took grams and used the molar mass to get the starting moles, right? So remember that when we are looking to determine limiting reagent, all we have to do is take one of those guys and basically figure out how much of the other one is needed to use it all up. So I'm going to take this guy and try to figure out how much sodium carbonate is needed to use that up. That is just a small little calculation here to figure that out. 0.0025 moles of calcium nitrate. Because we're doing our limiting reagent, we want to do the relationship between our two reactants, which happens to again be 1-to-1. It's not always, as you know, 1-to-1, but in this case it did work out all right. 1 mole of calcium nitrate gets us 1 mole of sodium carbonate. That's going to give us 0.0025 moles of sodium carbonate is needed in this calculation. That again is what we want to compare to our starting amount. And in this case, we need 0.0025 moles. We are starting with 0.003. That means we do have enough. And that's going to tell us that this guy is our excess reagent, and it's actually our calcium nitrate here, which is our limiting reagent. Remember, in a limiting reagent problem, the limiting reagent is the most important thing because that is the one that determines how much product you could form. So because we have our calcium nitrate in this case as our limiting reagent, that is what we want to use. So now we could actually do our product here. We're going to start with our limiting reagent, starting amount 0.0025 moles of calcium nitrate. That again is our limiting reagent, starting amount of it. We can now do the relationship between our limiting reagent and our product in this case. And it also is a one-to-one relationship. We've hit a lot of those today, so that's not too bad again. We're going to do 1 mole of calcium nitrate will give us 1 mole of our product, which is our calcium carbonate. That's going to give us 0.0025 moles of calcium carbonate. That is essentially our theoretical yield in moles. We're looking for the molar, our grams of it. So calcium is 4008 from the periodic table, 1 carbon at 1201, and 3 oxygens at 16 gets us 100.1 as the molar mass. So 0.0025 moles of calcium carbonate. Molar mass from the periodic table, 100.1 grams per mole. Moles are going to cancel. That's going to get us here about 0.25 grams, I think. And once again, since that is a product, that would be our theoretical yield in grams in this case. First off, any questions on that calculation there? So you can see you could have a limiting reagent problem in any situation, even with solutions, gases, regular sort of grams and moles. As you can hopefully see, it is still, as we've been saying, our same 4 steps: balanced equation, convert to moles. In this case, we did have to do the limiting reagent calculation, then continuing on with our limiting reagent to get to our product, and again, our moles to some other unit here. So again, basically the same 4 steps that we've done a number of times at this point in these type of problems. Any questions on any of that there? So the next type of really solution stoichiometry we're going to talk about is really a acid-base neutralization sort of reaction. It is really like titrations like you did in that experiment. So remember that when you do a titration, you basically add a solution of, say, known solution or known concentration to an unknown concentration. And you can use stoichiometry to basically figure out what is happening in terms of the molarity of the unknown. When you do an acid-base neutralization reaction, remember that ultimately you're making water. And that, again, is what the neutralization part of it is. And when you titrate to the equivalence point, that is the point in the titration where the moles of the acid equals the moles of the base. It essentially is the end of the reaction, if you want to think about it that way. And whenever you do an acid-base sort of titration, it is sometimes referred to as a neutralization reaction in a textbook type problem. And we basically use our same 4 steps. So let's take a look at this one here. What is the volume of 0.15 molar nitric acid that is needed to neutralize 45 milliliters of 0.55 molar potassium hydroxide? So this is really a titration problem. If you want to think about it, you can think about it this way. You're taking the KOH and you're adding it to the nitric acid right from the burette, basically, right? Looking for that light pink color change. We will need an equation in this case, so we're going to take our acid here, which is our nitric acid, going to react it with our potassium hydroxide, which is a strong base. Remember that whenever you take a strong acid and strong base, or just an acid and base, usually in general, you will usually get two things. You will get water that is formed. The water basically comes from the H and the OH there from the acid and base. This is really a double displacement reaction. And these two guys are going to switch partners basically. And that's going to give you a salt, which is KNO3 in this case. So that's basically our water and our salt. Remember that basically a salt is just an ionic compound. Now we could really just at this point, once we have the equation, we could just think of it as a stoichiometry problem. So obviously I just balanced my equation. In this case, we're looking for the volume and we have the molarity. Here we have the volume and we have the molarity. Bless you. And in this case, and I would say probably most cases when you're doing a titration problem or a problem like this, it's not going to be a limiting reagent problem. And we know it's really not because here we can get to moles, we cannot here. And by the way, we're looking for something about the other reactant, so it's definitely not limiting reagent. So it's just a basic stoichiometry problem really at this point. We're going to convert this guy into moles. So our moles of KOH is going to be converting our volume into liters. We want to divide it by 1,000. Move the decimal place 3 places to the left there. We're going to use our molarity just like it is, 0.55 moles per liter. We're going to multiply on top, divide on the bottom. That's going to get us here 0.045 times 0.550. 0.045 times 0.550. Try that. 0.02475 moles of KOH. Remember that if we are looking for the molarity of the HNO3, we need moles per liter. So we already have the molarity. We are looking for the volume. So we are really using, in this case, stoichiometry to get to the moles of the nitric acid. And we could do that by just going to the equation. In this case, the relationship between these two is a 1-to-1 relationship. So we will do 1 mole of KOH, 1 mole of nitric acid. You will get that to go away. You'll end up with 0.02475 moles of nitric acid. We now have really everything we need for the nitric acid here to figure out the volume. I am going to take a dimensional analysis approach, so remember that we can flip the molarity on its head there and use it in the other direction as a conversion factor as well. So taking this dimensional analysis approach, I don't have to think about rearranging this equation correctly. I just need to do opposites cancel. So that would put my moles on the bottom, my liters of nitric acid up on top. Moles are going to cancel. Once again, we're going to multiply on top, divide on the bottom, and we're going to divide by 0.150. Going to give us 0.165 liters of nitric acid. And if you want milliliters, you're going to multiply, in this case, by 1,000. And that'll give us 165 milliliters of nitric acid. In this particular problem, they really didn't specify the unit of the volume. So you could have left it in liters if you wanted to, or you can convert it to milliliters in this particular case. So even though this is a titration problem, still the same stoichiometry steps. Balance the equation, convert to moles, mole to mole relationship, and convert those moles to some other unit. Question on this. You are expected to show the work this way. You should not use the dilution equation. This is not a dilution, really. You shouldn't use it. You will get lucky in this particular case because the relationship is a 1-to-1 relationship. But if the molarity the mole-to-mole relationship between your acid and base is not a one-to-one, you will get the wrong answer. So this should really only be used for a dilution. It should not be used in titration problems, especially if you want full credit. Yeah, so make sure you show the stoichiometry part of it, and you will get the wrong answer. And sometimes you will see people call that the titration equation, but it is only for a specific situation, which is a one-to-one relationship. And if it's not, you won't have the right mole-to-mole relationship, and you won't get the right answer. Yeah. Any questions on that there? All right, why don't you try one here then? What is the volume of 0.355 molar sodium hydroxide that's required to react with 125 milliliters of 0.5 molar sulfuric acid, which is really just a stoichiometry problem. So again, we are not given any equation, so you got to start with that. Sodium hydroxide is NaOH. Reacts with sulfuric acid, which is H2SO4. Again, I know it's that because ic is 8, right? So that sulfate is basically the guy that's there. This really is, again, going to be a double displacement reaction. We have an acid and base. We should form water here. And it is the sodium here that's +1 and the sulfate that's -2 going to come together. And that's going to give us Na2SO4. Once again, always want to start with the correct formulas. Now we could balance it. I feel like I need some 2's somewhere. Where do I want some 2's? How about a 2 there? And maybe a 2 there should balance it up, I think. At this point, we can really analyze the stoichiometry part of the question, which is we want the volume here of sodium hydroxide. We have the molarity given to us. Again, I'm just going to convert it into moles per liter. We have for sulfuric acid the actual volume, and we also have the molarity of that guy given to us. Once again, not a limiting reagent problem because that is the only one I could get to moles from. Just makes it a basic sort of problem. We're going to convert this guy into moles because that's the only one we could do it with. So 0.125 liters, again dividing the milliliters by 1,000 here to get us there. Going to use our molarity the way it is written, 0.5 moles of H2SO4 to liters. Liters are going to cancel. That's going to get us 0.125 times 0.5, 0.0625 moles of H2SO4. Although we do have moles of H2SO4, it's not going to do us much good because we do need to get over to sodium hydroxide. And we think about our sodium hydroxide, we're looking for the volume. We have the molarity. So really what we're doing right now, again, is trying to use stoichiometry to get to the moles of sodium hydroxide. And that's what we could do. In this case, it is a 1:2 relationship there. So that's kind of important. So in this case, we're going to do our 1 mole of H2SO4 are 2 moles of sodium hydroxide. That will then get us 0.125 moles of sodium hydroxide. At this point, we now have what we need to figure out the volume. I'm going to use my sodium hydroxide here, molarity in the opposite direction. Again, so I don't have to worry about rearranging equations. I could just put the moles on the bottom so everything cancels out correctly. And in this case, our moles will cancel. And that's going to get us here, if I hit the right button, maybe. 0.352 liters of sodium hydroxide. Once again, we could convert that to milliliters if we wanted to by multiplying by 1,000. Gets us 352 milliliters of sodium hydroxide. Once again, in this question, they didn't really specify the units, so you could leave it in liters or milliliters. Any questions on that one there? Again, it's the same 4 steps. Balance the equation, convert to moles, mole to mole relationship, and moles to some other unit. By the way, right here is also why you cannot use M1V1 equals M2V2 in this case. You will be off in terms of your stoichiometry there and your mole to mole relationship. All right, one last one here to wrap this chapter. In a titration requires 63.5 milliliters of 0.375 calcium hydroxide to reach the equivalence point. In a titration, 95.5 milliliters of hydrobromic acid. What is the molarity here of the hydrobromic acid? So take a moment and figure out the molarity. Again, okay, so let's take a look here since we're getting to the end. Again, we're going to start with our equation here. So calcium hydroxide, calcium is +2, hydroxide is -1. So again, we want the proper formula here when we put that together. Hydrobromic acid, hydro means there's no oxygen, so it should look something like this. Again, it's still a double displacement reaction. We should always make water. And in this case, it's going to be the calcium and the bromine coming together. And again, calcium is +2, bromine is -1, so we will end up with a CaBr2. We're going to balance our equation here, so put a 2 there, and I think a 2 there to balance it up. Any questions on the equation there? At this point, we can look and see what we got going on. We have information about our calcium hydroxide, 63.5 milliliters, 0.375 moles per liter. We're actually looking for, I believe, the molarity of our HBr. And we do have, in this case, though, the volume, 95.5 milliliters. So although it's not converted yet, we can get the liters from that. That means we could again use stoichiometry here to get to the mole, so we could calculate the molarity. So just like all the other ones here, we're going to convert this guy into liters, divide by 1,000, move to decimal place, 3 places to the left. We're going to use our molarity of our calcium hydroxide the way it's written so that the liters will cancel. Liters will cancel. We're going to multiply the top, divide the bottom. 0.0635 times 0.375 gets us 0.0238 moles of calcium hydroxide. Once again, we need actually to get over to the HBr. So that is where the stoichiometry comes into play. It is a 1 to 2 relationship between those two from the balanced equation. So 1 mole of calcium hydroxide gives me 2 moles of HBr. That is the stoichiometry part here. And we'll times that by 2. Gonna get me 0.0476 moles of HBr. That is really the sort of last thing that we need there to do our molarity calculation, but since it is molarity, we do again need to convert our volume into liters. So in this case, we're going to once again divide by 1,000 to do so. And that really is what we want to divide our moles by so that we could get it into molarity in this case. That will give us, looks like 0.499. The units here don't cancel, so it is moles per liter of HBr. At this point, since the calculation is over, you could also go back to the big M, if you like. HBr in this case. Either way would be an acceptable way. So in this case, again, our same 4 steps: balance the equation, convert to moles, mole to mole relationship, and convert those moles to some other unit. So we've seen here you can use solution stoichiometry and end in grams. You could use it to figure out the volume, and you could also, as you can see here, use it to figure out the molarity. Any questions on any of those there? Yeah. Hopefully